What is the science behind creating giant rockets that can lift hundreds of tons of matter out of Earth's gravity using only liquid fuel? Let's learn and analyze this issue more closely. Remember to subscribe to the channel to learn more about the latest scientific knowledge. Lifting hundreds of tons of mass out of Earth's gravity is a physical marvel. And the secret lies in liquid fuel. The massive rocket operates based on Newton's third law of motion. Every action has an equal and opposite reaction. To propel the colossal rocket mass, the engines must generate an opposing force stronger than gravity, which is thrust. This thrust comes from the extremely rapid and powerful combustion of liquid propellants inside a confined chamber. Most large rockets use liquid oxygen and liquid hydrogen, chilled to extremely cold, cryogenic temperatures. These two substances are injected into the combustion chamber via turbopumps, components that spin at extremely high rotations per minute. The turbopumps are essential for forcing vast amounts of fuel and oxidizer into the combustion chamber, where pressure is incredibly high. This is where the magic happens. The liquid oxygen and liquid hydrogen react, producing a huge amount of superheated, high-velocity gas. This hot gas is channeled through a specialized design called the Laval Nozzle to maximize its speed. The nozzle acts like a horn, turning high pressure into immense velocity, generating colossal thrust. The rocket must generate thrust greater than its total weight from the very first moment to be able to lift off. The difficulty is that the rocket must carry nearly 90% of its mass as fuel, making it immensely heavy. Engineers must design the rocket body and fuel tanks to be incredibly lightweight yet possess very high structural strength. As the rocket climbs, it discards sections where the fuel is spent, known as staging, to shed dead weight. The staging process is critical, ensuring the remaining engine thrust is always stronger than the decreasing weight. A huge challenge is the heat. The combustion chamber reaches thousands of degrees Celsius, hot enough to melt any metal. To counteract this, engineers use regenerative cooling. Unburnt fuel is circulated to cool the engine chamber walls. This preheated fuel is then injected and burned, which helps increase the overall efficiency of the entire engine system. During flight, the engines must have the ability to swivel slightly, gimbaling, to steer the rocket and maintain a precise trajectory. The control system must continuously calculate gravitational pull, atmospheric drag, and adjust the thrust every millisecond. Once the rocket escapes the thick lower atmosphere, it no longer has to fight against air resistance. However, it must achieve escape velocity or orbital velocity to prevent the Earth from pulling it back down. Orbital velocity is roughly 28,000 km per hour at low altitude. This is the ultimate goal of the engines. Liquid propellants like liquid oxygen and liquid hydrogen provide a much higher specific impulse than solid fuels. Specific impulse is the measure of the engine's efficiency, indicating how much thrust it generates per unit of fuel consumed. High efficiency is the key to delivering large payloads into orbit with a feasible amount of propellant. The fuel tanks must have slosh baffles, which are internal structures that prevent the fuel from shifting excessively during acceleration. Another challenge is cavitation, bubble formation, in the turbopumps due to the low pressure of the supercold liquids. Engineers have designed complex turbopumps with different stages to meticulously control the fluid flow. Precision in manufacturing the valves and plumbing is paramount to prevent leaks or freezing. The entire rocket must be built with redundant guidance systems to prevent mission failure due to a single equipment malfunction. Highly sensitive sensors, like gyroscopes, help the rocket know its exact position and orientation in three-dimensional space. After completing the push mission, the upper stage will shut down its engines, and the payload will be safely separated. The engines designed for the upper stage are typically optimized for the vacuum environment, featuring much larger nozzles. The larger nozzle in a vacuum allows the exhaust gas to expand maximally, adding more thrust. The combination of powerful engines, efficient fuel, and lightweight structures has turned these massive rockets into reality. It is the science of thermodynamics and mechanical physics that creates the miracle of space cargo transport. The combustion chamber design must ensure complete and stable burning of the fuel, without dangerous pressure oscillations. Excessive vibrations can lead to a phenomenon called pogo oscillation, which can structurally compromise the rocket. Therefore, Damping devices and pressure regulators are integrated into the propellant system to control this vibration. Modern engineering also allows for rocket engines to be reused, saving costs for future missions. This reusability requires the engines to be designed to be much more durable, withstanding multiple burns and landings. In summary, creating the necessary thrust is a complex interplay between advanced materials and extreme combustion engineering. The gigantic launch vehicle is the strongest testament to the power of applied physics and precision engineering.
If you find this video useful and want to explore more interesting things with me, don't forget to like and subscribe to the channel. Now, goodbye and see you again in the next videos.